Imagine a chemical plant that can predict equipment failure before it happens, reduce energy consumption automatically, and continuously optimize production quality, all without human intervention. This is no longer futuristic, this is AI driven process optimization, which can result in higher efficiency, lower energy cost, and fewer downtimes. Hello everyone, welcome back to Chemical Engineering and Aspen channel. In our previous video, we discussed the applications of artificial intelligence in chemical engineering, and this is the part 2 of our video related to applications of AI in chemical engineering and how artificial intelligence is transforming real chemical plant operations. Obviously, the process optimizations play a vital role, and integrating AI using its tools such as machine learning and digital twins are really important once we talk about the artificial intelligence applications in any field or in the field of chemical engineering. Now, why process optimization is challenging? Because once we talk about the systems or the dynamics of the process, usually in calculations or in studies, we assume linear systems. However, these are nonlinear systems. These have strong variable interactions like effect of temperature, pressure, flow rate, composition, level, and continuous disturbances in feed and operational conditions. We assume steady state, but in real practice, the systems are not steady state always. There is some fluctuations happening in the system, though these may be minor, but still there are some fluctuations which we need to handle. Secondly, the equipment degradation, such as heat exchanger fouling, reactor temperature variations, distillation purity variations over the time, often these are unpredictable. And then the sustainability pressure that we have to make sure that our energy requirements are within the constraints or within the targets, and similarly, our emissions requirements as per the international standards are within the range. Obviously, for this, we need to operate plant closer to their optimum, leaving little margin for error. Once we talk about the traditional optimization techniques, these are not sufficient alone once we talk about the modern plant operations. So obviously, we need to introduce the AI to ensure that we get more process optimization. If we talk about the traditional methods, that why they are not suitable or alone efficient for today's world, these are first principle models or empirical correlations which are designed for slower, steadier work. However, in today's day, we need to be fast. We need to be more aggressive in our approach. Aggressive means that we need to be more adaptive, data driven, such as using the tool AI. Now, what are the issues of traditional methods, such as it is computationally expensive, not real time ready, and limited adaptability? So, these three limitations introduce the concept of artificial intelligence and its integration in the real world systems. Where AI fits in chemical engineering is another important aspect that engineers must know, students, researchers, professionals must know so that they can apply it. For example, in pattern recognition, that the artificial intelligence can recognize or can identify the variations of a certain variable on the process conditions, like the effect of temperature or effect of composition of a particular component, so on, like these parameters. Then it can predict real time data, that it can predict how quality compositions can vary and how to control these. And obviously, for this, it needs to have automated decision support, that it can change or it can recommend the changes in the set points, flags anomalies, and escalates alerts without human delay. That it does not wait for the humans to act, it in fact takes the decision and implement it. And finally, the adaptive control, that continuously retrains on new data to maintain performance under changing conditions. Because with the evolution, obviously the models should be trained and these should be able to adopt with time. Now, machine learning models which can be used or which are used in the industry, there are three models which we talk about. Number one is the regression model, and in the regression model, it could be linear regression, random forest, XGBoost. These are fast, interpretable, ideal for steady state prediction and soft sensors. Number two is neural networks, which is ANN, artificial neural network, deep learning, LSTM. These capture the non-linear dynamics and temporal dependencies in time series process data. Number three is reinforcement learning, that it develops autonomous control policies through trial and reward. And it is suited to dynamic optimization under uncertainty. So for different processes, we may need regression. For different processes, we need neural, or maybe for much more complex systems, we could go for neural or reinforcement learnings. Now we will one by one discuss the applications of AI. So for this, the first application is heat exchanger fouling prediction. Obviously, we know that fouling degrades the heat transfer efficiency within the heat exchanger, obviously increases the energy cost, and could, in worst case scenario, could cause the shutdowns, and obviously with little warnings. Now, in AI solution, obviously the models are trained to ensure that they predict the fouling trajectory, enable data-driven cleaning schedules instead of fixing in the maintenance or downtime. Now, once we have integrated AI, it will reduce downtime, it will increase efficiency, and it will lower down the maintenance costs. Second example is related to the distillation column optimization, that we have to, obviously in distillation column, we want that our purities are achieved. We do not have to spend too much on the energy cost. Like balancing product purity against steam and reflux consumption is a continuous multi-variable challenge. Obviously, there is not a single variable in the system. There are multiple variables which we have to control, and one where AI delivers measurable gains. Now, once we have implemented AI like neural network soft sensor, it can predict the tray temperature and compositions in real time, feeding an optimizer that can adjust the set points dynamically to ensure minimum energy consumption but without compromising the purity specifications. So once we have controlled our energy savings, like in reboilers, we have reduced steam and reflux consumption, and obviously we have ensured that our purity controls are there. And obviously there are few off-specs conditions. Then number third application is predictive maintenance, that obviously AI can monitor what humans cannot. Like it can monitor the failure signals before the breakdown or before the shutdown. So what it will do, it could do the vibration analysis, it could do the thermal trending, that it could measure the data of temperatures and accordingly pressure anomalies. So it could track the data of the real-time process parameters and can sense that now at this stage it needs to be, or that flange or that valve or that thing needs to be replaced, to ensure that predictive maintenance has been done before the actual plant downtime, and it will obviously save the energy cost. Now, once we talk about the digital twins in chemical plants, for digital twin synchronizes a high fidelity visual model with a live plant through sensor data and AI. Now you can see that this is the physical plant that is operating here. It is now on the DCS. Then through AI, its insights and controls are measured, and then accordingly the measurement and accordingly implementation on the physical plant. So physical plant, virtual model, this one, then accordingly AI layer and the suitable control techniques are applied to ensure that the plants operate in the best possible way. So it can be categorized into four ways. Number one is the real-time simulation. Number two is what if analysis, effect of parameters on the process, the operator training, and performance optimization. Now, the key takeaways from this lecture is that data-driven models often outperform static correlations. Number two, industrial applications are proven and expanding, like we have discussed, the fouling, the distillation column, the predictive maintenance. And number three, digital twins close the loop that by combining the live sensor data with AI-powered simulation, plants gain faster decisions, safe operations, and higher productivity. The future of process optimization is adaptive, predictive, and intelligent, and it is already here. AI is transforming chemical plants from reactive systems into intelligent, adaptive systems. In the next lecture, we will explore how chemical engineers can start learning AI tools like Python, TensorFlow, and Aspen integration. So I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer it. So that's it from today's lecture. Thank you so much. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.